Oh, hi there. Welcome back to INF 52670. In this lecture today, we'll look into containers. If you're not familiar with that, it's something that has really revolutionized the way we build and deliver applications. And there are many really good uses in IT, admin, DevOps, and so on. So yeah, we're gonna have a hands-on activity after this class, after this lecture. So we're gonna do that together later. So just some inspiration. So basically, what is a container? A container in general, right? It's just a, so I'm talking about containers in general. Um, what can you do with a container? Well, you can ship anything. So you can load it with anything you can imagine, with cars, with electronics, oil, grains, right? Anything. And then do I worry about how goods interact? Coffee beans next to spices and so on, right? So we just load that container with things and it's delivered, right? But then what is important here is that there is an ecosystem around containers, right? To make it more efficient when you are loading, when you are putting this on transportation system like a truck or a train or a ship, right? So you can stack them. There are many standard and standardized machines and everything around this ecosystem to make it more efficient, right? For the delivery of goods. Um, so So in the past, we just some images to show you. In the past, we would load ships, right, and cargo ships like this, right? We have our, for example, our bags of grains, coffee, whatever, and we would have a lot of workers, sometimes even slaves, right? Um, so getting one by one, putting on the ship on ramps, very inefficient, time consuming, right? And today we have something like this. Like I said, it's a complete ecosystem around shipment of containers, right? And so it's so optimized, and all the machinery for that purpose, right, was developed. And so 90% or more of all cargo ships in containers today. So like I said, there is, you know, a reduction in cost and time to load and unload containers. It's very optimized, right? It's a massive reduction in losses, huge reduction in freight cost. You are shipping, well, your shipment, your everything around it. It's much more efficient, space, everything, that it makes it much cheaper, right? And then all that led to the globalization, right? So So what is a container then? Okay, containers are modular environments that allow you to run resource isolated processes together to deliver an application. Again, a container will be a stripped down VM, okay, with everything needed to run your application, and then it shares the kernel, the OS, the guest OS, the host OS that is running underneath. It'll share with all the other containers. Okay, so it makes it very lightweight. So, but what I want to show here is that it's modular, and then you can pack a container with whatever application you need to, or the pieces of that puzzle you need to run your application. Okay. Containers are defined by config files. You will see in the hands-on exercise and the activities how we can build a container. There are some different ways, but one of them is using a config file, which is the most common of them. So of which can be deployed anywhere to reproduce an exact copy of the original environment. So you can have multiple copies of that. You can develop or you can put together a web server, all configured and everything in place. And then when your customers or clients or your team within your organization, they need a web server, you have one right away. You just deploy in whatever machine you're running, or you can even deploy at the client's machine. It's really cool. It's really interesting. So it's great for web application development, clusters, DevOps support, etc., etc. There are many applications for that. And in another lecture, we'll talk about microservices and see other examples of applications. So a container, so in a more technical view, is an engine that enables any payload to be encapsulated as a lightweight, portable, self-sufficient container. It has everything in that to run the application, okay? That can be manipulated using standard operations and run consistently on virtually any hardware platform. Like I said before, since it shares the underlying kernel, it's lightweight, and also it's like a VM. It's a file. So you can do anything you do with a file. You can do with containers. Copy, delete, move. Now, a good question, right, is how do you compare? What is, how do you compare containers and virtualization? They seem to be the same, right? Well, yes and no. All right. So remember, virtualization provides true isolation, right? And between the VMs by abstracting and constraining underlying resources. All the resources are, you get CPU. They are isolated, and one VM will think it's using the hardware. It doesn't even know it's virtualized, but that resource is isolated for that specific VM and then for the other one and the other one, right? All VMs, they have their own resources and their own OSs. Now, containers, they are not a full VM, it's not a full OS running in that container, but they are simply processes that run in a resource-constrained environment. Like I said before, they share the host OS kernel. We discussed about the hypervisors, right? The OS-assisted hypervisors. So there you go. They share that kind of hypervisor OS, right? They share host binaries. Container images are very small for that reason, right? Again, a VM will contain all the OS and its files, which can be gigabytes in size, right? Just imagine if you have a pre-configured web server in a VM. Well, you will need the OS, the software for your web server, and many other things, right? Just the OS will take most of the space, right? It could be lightweight Linux, but still quite large, right? So it could be 1 gigabyte easily. Okay, now a container will be very small because it doesn't contain the entire OS, right? That's why it's interesting. It shares the kernel with all the other containers. It's very lightweight, and for that reason, there are some benefits. We'll discuss them in a moment. So they have their own file system, all right? With chroot. Chroot provides that the file system, so it has the hierarchy, the directories, as a full OS, and it shares the underlying physical resources through the host OS, right? It'll make sense when we start implementing this, okay? So don't worry if it's still vague. Sometimes a concept doesn't click at first, but it will when we get to work with it, all right? So basically a summary and a comparison of containers and VMs. So in a container environment, like I said, you have your physical resources, your infrastructure, you have your host OS, and then in this case, I'm talking about Docker. You also have others like Kubernetes and others, right? But they are very popular. Docker is very popular as well. So this is a container. It'll have an application, right? Usually we isolate one application in a container. And then the bins, the libs, and all the binaries necessary to run the applications. And then obviously through this, all these containers here, they share the OS, and they are lightweight, like we discussed before. Now in a VM, as you know, you have, within a VM, you have the applications, right? You have all the file system and everything, and you have an OS together, the full OS, right? It is a full machine, a virtual machine. And then they share the resources through a hypervisor. The hypervisor is responsible for the emulation and the distribution of the resources. Okay, so that's the basic difference. So we have one layer here, which is the container environment, in this case Docker. All right. we can have container nesting. So you have more than one application and file system, more than one application within one container, right? It's what we call container nesting. All right. Yeah. So now it comes to the point where what are the benefits then? Well, we know some, right? We've discussed some that, for example, containers are smaller. Okay, but okay, what does it mean? What is the benefit of being smaller, right? Maybe it's slower, I don't know. Okay, let's take a look at that. So there is an environment consistency. So containers provide portability, reproducibility. All environments are defined in an environmental configuration file. When you run it, it doesn't matter in which machine, in which OS, it comes from a config file. So your containers will always be consistent, they will always be identical. All right? A container deployed on Amazon Cloud, AWS, is exactly the same when it's deployed locally or on a private cloud or any other cloud. All right? Operational efficiency. Containers are grouped together strategically since each is an application space. That means you can have multiple related applications to run together on a single host while still being resource constrained, while still being lightweight. Okay? It'll make sense when we start implementing. So other benefits include increased developer productivity. That's kind of obvious within the container environment. So environmental consistency removes cross-service dependencies for applications. So for that reason, applications can be broken into individual components where each process runs in its own container environment. They are separate, but all working together for a bigger application, right? For example, a web application with Nginx or Nginx and database with MySQL, right? Running separately. And because of that, there are other benefits we'll discuss in a moment. Version control is another benefit. Since all application environments are defined by files, entire environments can be version controlled using all the different tools and standards, SVN, Git, etc., etc. Okay. So let's take a look at some use cases for containers. Distributed applications, it's one of the main domain of applications that will benefit the most from containers, because you can break apart a web service, for example, into its components, of which will all scale individually. All right, that's why it's really nice and neat, this concept, this container concept, that it gives you the flexibility to run them separately, and then you can scale. For example, you can have MySQL, Nginx, RabbitMQ, and load balancers, and running separately in separate containers, not on the same server, not on the same VM, or different VMs, which are heavier, right? So you will see later. And then because they are separate, you can scale them according to demand. You can scale them separately. All right. And then microservices. We'll have another lecture on microservices. They allow hyper-scaling horizontally through reproducibility. One example, scaling an Nginx instances of a website horizontally across 1,000 containers. And now you will see the benefit of being lightweight, small, when compared to VMs. All right. Batch processing is another interesting domain that can benefit from containers. So when you have compute-intensive applications, they can deploy thousands of container nodes to provide great computing environments. Bitcoin mining is a good example of that. Continuous integration. Since containers can be version controlled, it's possible to automatically deploy environments by pulling new containers from Git and deploying them automatically to a cloud environment without requiring developer intervention. Again, automation. You have a new version, you have an improved version of that application running in a container, right? It's a file, right? So you can just pull it from the repository and update it automatically. Can also pull to a development environment for testing. Again, it's a container, like in a real container where you can move it around. So you can move it to a development environment for testing. Now let's take a look at types of containers. I mean, the different vendors or flavors. We've been talking about Docker, right? We'll have hands-on on Docker. It's very interesting. So container, what is Docker, right? It's a container-based virtualization tool that assists developers in quickly developing, deploying, and running applications. Like we discussed before, containers are isolated, may or may not have resource restrictions, have their own file system, and share the host kernel and binaries. This is common for all containers, but Docker also just follows the standard, right? This is done using namespaces and C groups. If you're familiar with Linux file systems, we'll look into that later. And containers run as an isolated process. A container will be an isolated process, okay, using Docker. Who uses Docker? Well, GE, PayPal, ADP, XP, etc., etc. All right, there are many companies using Docker today. Even many applications using Docker that we don't even know. Okay, it's transparent to the user, anyways. So let's go a little bit deeper into Docker and see what it's how its components and all the other details. So In a Docker, it's a simple piece of open source software running on a Linux server. All right, act as a software intermediary for Linux namespace, C groups. LXC, we will discuss LXC in another lecture. IP set, IP tables, etc., etc. All right. Provides a remote API for the Docker client software. So this is the Docker. And then the Docker client software, either the Docker app running on the actual server or a Windows OS X applications that connects to a remote Docker server. And we also have another component, which is the Docker Hub. It is a software as a service platform for sharing and managing Docker containers. So it's a repository where you can just pull and save and push containers into it. All right. We'll also work with Docker Hub. So just a few more, a little bit more details about Docker and its architecture. So you have your Docker client, Docker run, Docker images, for example. It will call the Docker, the executable. So then, for example, you have in Windows and Linux, you will have a daemon, the Docker engine in both OSs. And then here you have a Windows Server container support, and you have Linux container support called LXC, which is how Docker evolved from LXC, and well, we'll discuss that in a moment. And then there is the Docker Remote API with get and post. For these are one example: get images, JSON, containers, create. Again, when we start implementing this, then it'll make more sense. All right, working with Docker. Again, Docker versus VMs. So a virtual machine, again, you have your applications, you have your binaries, your files, your file system, you have your OS, right? I mean, all the files necessary to run the application, and you have your OS. Each virtualized application includes not only the application, which may be only tens of megabytes, and the necessary binaries and libraries, but also the entire guest operating system, like we discussed before. And it runs all on the hypervisor. The hypervisor is responsible for managing all the virtual resources and interfaces with the VM. It's the interface between VM and physical hardware, physical resources. And then Docker, a container, which will have only the application and its files and binaries necessary to run the application, running over a Docker engine that runs on the host OS. Okay, the Docker engine comprises just the application and its dependencies, like I said. So it's much lighter than a VM. Okay. So, images, what is a Docker image? They are pre-created Linux environments with file system, configurations, and all the binaries necessary to run that allow the execution of commands in their predefined environment. You will see, guys, when we get into a container, you can go in the container, open it, and you can, SSH, you can run commands in command line. It's a full environment there. So you can do anything in that little container. run other things, connect to other things, other containers, for example. It's really interesting. Important images are read-only. Okay, once a command executes, all changes are lost. So whatever you run in that container will be lost later. All right. And a container, it's a temporary running instance of an image. So you have the image, and you can have multiple instances of that image, which we call the container. All right, just a copy, an instance of the image. Example, if you execute a command on an image, a container is temporarily made from the image to run the command and is removed when the command finished executing. All right. One example of a Docker file. So don't worry if it's, well, if you're familiar with Linux, you will see it's not too complicated, but we'll have a we'll build a web server in a container, run it, and do many things with it, many operations on that. And you will see it's going to be very simple. And of course, you can build on top of that. But basically, you have what I want to say is, when we get to the hands-on, then I'll go into detail of what each command will do and things like that, okay? But don't worry, for now, it's just to give you an idea of what a Docker file, a configuration file for Docker looks like. So then you can run apt-get, for example, update, install. In this case, it's installing this, right? Like you would do it in a Linux environment, right? So it executes line by line. When you instantiate that image and then you have a container, it goes through this and executes this. So that's why we're talking about the consistent environments and so on, because they come from this file and they will be identical, right? What else? Well, displaying the port, well, throwing the port 443 to this file here, etc., right? Creating a directory here, changing the permission, and then it runs that application, expose the port, right? We'll go into details about them. It's just to give you an idea of what it is, of what a Docker file is, okay? Now, LXC, LXD. LXD takes the speed and latency of containers and brings them to the hypervisor world. A LXD container gives you a full machine system functionality, not just a simple process. Okay, you can run Docker and LXC inside LXD to mix container types. LXD is a really fast hypervisor that lets you operate exactly the way you currently operate, only at container speeds. So it's another type of container environment. Actually, Docker runs on LXD, and this Docker was an evolution of LXD, LXC. So LXC is the core container service itself, whereas LXD provides the API overlay to facilitate the additional orchestration and functionality on top of the container service LXC. Again, open source and ships by default on all modern Ubuntu systems. Resources are constrained using C groups, namespaces, AppArmor, seccomp, etc. LXD Container supports almost all Linux versions as guest operating systems. Remember, they all use the same shared host kernel. All right. So, what are the features of LXC, LXD? So, bare metal performance or close to that, right? Very precise quality of service and quotas, snapshots and live migration of containers, support the different processor architectures, rapid provisioning, instant guest boot, remote image services like the Docker Hub, extensible storage and networking, and more. We're not going to go into details of LXC, LXD in lectures, but you will have a lab on that, which is everything will make more sense. Okay. Who uses LXC, LXD? Walmart, Box, PayPal, etc. There are many companies using that. Now, let's just take a look at Docker and LSD, all right, or LXD, LXD. Docker runs single processes. LXD provides a whole guest OS, right? That's the main difference. LXD provides you with supportive services like logging, SSH, etc., whereas Docker only runs a single application. All right, think about LXD as really close to a full virtualization kind of thing, and Docker is simplified and runs only that application. All right, and for microservices it is a plus. Docker supports DevOps and platform as a service deployments, whereas LXD is more focused on IaaS, okay, infrastructure as a service. You can run Docker on LXD. It's a hypervisor, okay? So as a Docker is just an application wrapper service, this also has almost zero performance impact. Okay. Now, let's take a look at some examples of containers being offered by public clouds, right? You have the container environment, right? So you have the Amazon EC2 Container Service, Azure Container Service, Google Container Engine, Docker Cloud. There is also Docker. The Docker Engine is there together. Yeah, AWS Elastic Beanstalk, which can work with Docker, PHP, Java.NET, and so on, so on. All right. Container security, interesting topic. So, as I mentioned before, LXC over LXD, it relies on C groups and namespace for isolation. You can have quotas, right? Resource quotas using C groups, but you cannot enforce them. One example, if a single container uses all inotify handles in the kernel to track file system changes, systemd on the host will fail. This is one example of container security. Some resources cannot be constrained, for example, disk I/O. All right, so it can pose a security risk there, right? Kernel modules loaded on the host pass through to all the containers. So if there is a problem, remember it has to go through all the layers, right? Exploiting the kernel of a container potentially exploits the host. Again, the container uses the host kernel, so it's not fully isolated. What I want to say is that it's not fully isolated like a virtual machine, a VM. Okay, that will, if there is a kernel exploitation in a VM, it affects only that VM, right? Not in the case with containers. So public LXD images could be preloaded with malware. You will see, even with Docker Hub, when we go to the repository, you will see the ones that are official or they were checked. And well, you know, what I want to say is you may find malicious containers and you don't even know. They say, hey, this is an Apache server, okay, and then you use it and it's compromised. All right, so you have to be careful with that, but you'll see in Docker Hub, and we'll come back to this discussion later. Docker. Resource quotas are enforced by the Docker service using namespace and C groups like LXD. Memory, I/O, and process forks are hard to constrain, like LXD. Running out of UIDs, for example, will affect all the other containers. Okay. Kernel panics in a Docker container cause host kernel panics. Again, they share the kernel. Kernel modules loaded on the host pass through to all containers. Exploiting the kernel of a container potentially exploit the host, like we discussed before. It's the same thing with Docker. Public Docker images could come preloaded with malware, like I discussed with Docker Hub. Okay.